Now we come to the one of the most important law or most important statement in physics. That is the relation between the entropy and the second law of thermodynamics. In the beginning of this chapter, we talk about the second law of thermodynamics in terms of the impossible to build the heat engine that can change all the heat from the hot reservoir solely to the work without any waste of the heat to the environment. We also say that we cannot build the refrigerator that can take the heat inside the refrigerator out to the hot environment outside the refrigerator without the input of the mechanical work. Now, we have the concept of the entropy, and we say that the entropy is related somehow to the disorder of the system. We have shown that in the Carnot cycle, with our process are reversible, the change of the entropy is zero. We state that in general, the entropy of the cyclic reversible process is equal to zero. Okay. Now we will generalize this concept to the another form of the second law of thermodynamics. That is, we can say that the entropy of the universe increases in all real processes. It means that if we have a system, if the system is closed, so we may say that that is the universe, any process inside the system will increase or at least not change the entropy of the system. We can say that in any closed system, the change of the entropy is larger or at least equal to zero. It means that you cannot reduce the entropy of the system if the system is a closed system. Okay, if it is a closed system. If it is an open system, you may have that if you have the system 1 and it interacts somehow with the environment, or maybe we can say that it's a system 2 and these two systems form a closed system. Somehow you may find that the entropy of the first system reduced. But if you calculate during the process that the entropy of the first system reduced, there is the interaction between the first system and the second system. And if you calculate the entropy change of the second system, you will find that the change of the entropy of the second system is larger than zero. And the important thing is that if you combine the change of the entropy of the whole system to get the net change of the entropy, which is equal to the change of the entropy of the system 1 plus the change of the entropy of the system 2, it will always greater or at least equal to zero. That's why we call that the entropy of the universe increase in all real process, because the universe is a huge, big, closed system. Because everything is in universe, nothing is outside the universe. So, if you do any process, you may reduce the entropy in some part of the universe, but you will increase the entropy of the other part of the universe. And if you combine the net change of the entropy of the universe, you will find that it will increase or at least not change. You cannot have the process that reduce the entropy of the universe. Be careful. I say the entropy of the universe. The entropy of the subsystem in the universe may reduce, but if you calculate the entropy of the whole universe is always increased, or at least the process will not change the entropy of the universe. This statement can be proved in some sense using more advanced statistical physics or the statistical mechanics that is beyond the scope of our course. However, we can show some simple example that show these that show the result of this statement. For example, let's look at the entropy change in the thermal conduction. In this problem, we look at the thermal conduction between two reservoirs. There is a thermal conduction from the reservoir of the high temperature TH, and the heat goes from the hot reservoir to the cold reservoir with the temperature Tc. Okay. And we look at the change of the entropy of these two reservoirs. These two reservoirs will be maybe in the direct thermal contact, or maybe connect via some conduction of the medium. We assume here that the change in the entropy in the medium may be small, so we will concentrate on the change of the entropy in the reservoir itself. Okay. Since the reservoir is keep at the constant temperature, so if there is a heat Q that leave the reservoir, the hot reservoir to the cold reservoir, the change of the entropy of the hot reservoir is equal to the minus of Q over TH. This is, we use the minus sign here because we know that the heat leaves the hot reservoir, which means that it will reduce the entropy of the hot reservoir. You can see that the entropy can decrease in some part of the universe, but it's not finished now. Now, if we look at the change of the entropy at the cold reservoir, since now the heat Q enter the cold reservoir, so we have that the entropy change is equal to T over Tc, and we have the positive value here because the heat enter the system and it increased the entropy of the system. The change of the entropy of the universe here, the universe is the hot reservoir together with the cold reservoir. This is the universe. This is the universe. So the change of the entropy of the universe is equal to the change of the entropy of the hot reservoir plus the change of the entropy of the cold reservoir, which equal to the Q times 1 over Tc minus 1 over Th. And since Tc is smaller than Th, we have that 1 over Tc minus 1 over Th is positive. So you can see that the net change of the entropy of the whole universe increase. In some portion of the universe, the entropy may decrease, but it will increase the entropy of the rest of the universe, and the net change of the entropy is increased. It is interesting to do that. If we try to perform the impossible process, what will happen? For example, if we assume that we can transfer the heat back to the hot reservoir from the cold reservoir without the work, that is, heat go by itself from the cold reservoir to the hot reservoir. So in this process, you can see that we will have that delta U will be less than 0, which is impossible, because we know from experience that the heat will flow from the hot region to the cold region. We never see the heat that flow from the low region to the hot region. So we can safely say this is impossible. And when we look at the change of the entropy if the process occurs, you can see that the entropy will decrease, which guarantee that this is impossible.